Power factor is a measure of how efficiently electrical energy is being used. A low power factor indicates that a significant portion of the current is not contributing to useful power. This reactive current flows through the wires and equipment, causing losses and voltage drop. To calculate voltage drop with a poor power factor, use the following modified formula: voltage drop equals current times resistance times power factor. The power factor has a direct impact on the voltage drop. A poor power factor results in a higher voltage drop for the same current and resistance. This is because the reactive current is effectively increasing the impedance of the circuit. A good power factor reduces the voltage drop by minimizing the reactive current and thus the overall impedance. A very poor power factor can lead to increased voltage drop and voltage fluctuations, overheating of wires and equipment, reduced efficiency and increased energy costs, and potential damage to equipment. To mitigate the effects of poor power factor and voltage drop, consider the following measures. Firstly, use capacitors to improve the power factor by adding capacitive reactance to the circuit. Secondly, use power factor correction devices, such as synchronous condensers, to generate reactive power and reduce the load on the system. And thirdly, improve the overall system design to minimize inductive loads and reactive current. Let's delve into a more detailed discussion about power factor and its relationship with voltage drop. Power factor is defined as the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. It essentially represents how effectively electrical power is being used. An ideal power factor is one also known as unity, which means all the power supplied is used for useful work. However, in practical scenarios, especially with inductive loads like motors and transformers, the power factor is often less than 1. This is because these loads require reactive power to operate, which doesn't contribute to the actual work done but still draws current from the source. The presence of reactive power leads to a phase difference between the voltage and current waveforms, and the cosine of this phase angle is the power factor. A lower power factor implies a larger phase angle and a greater proportion of reactive power. Now let's examine how poor power factor affects voltage drop in electrical conductors. Voltage drop is the reduction in voltage that occurs as electrical current flows through a conductor. It's primarily caused by the resistance and reactance of the conductor. The formula for voltage drop, considering both resistance and reactance, is as follows: voltage drop equals current times impedance. Impedance, denoted as C, is the total opposition to current flow in an alternating current circuit and is comprised of resistance, denoted as R, and reactance, denoted as X. Reactance can be either inductive, denoted as X subscript L, or capacitive, denoted as X subscript C. In most industrial and commercial settings, inductive reactance is more prevalent due to the widespread use of motors, transformers, and other inductive equipment. The formula for impedance is Z equals the square root of R squared plus X squared. When the power factor is low, the reactive component of the current is significant. This reactive current contributes to the overall current flowing through the conductor, thereby increasing the voltage drop. To understand this better, consider two scenarios: firstly, a circuit with a high power factor, close to 1, and secondly, a circuit with a low power factor, say 0.7. In both cases, assume the same amount of real power is being delivered to the load. In the high power factor scenario, the current is mostly in phase with the voltage, meaning most of the current is contributing to useful work. The reactive current is minimal, resulting in a smaller voltage drop across the conductor. In the low power factor scenario, a significant portion of the current is reactive, not contributing to useful work. This reactive current still flows through the conductor, increasing the overall current and consequently the voltage drop. The increased voltage drop can have several adverse effects on electrical systems. Firstly, it can lead to reduced voltage at the load, which can cause equipment to malfunction or operate inefficiently. For example, motors may overheat and have reduced torque, lighting may dim, and electronic devices may not function correctly. Secondly, excessive voltage drop can cause increased energy losses in the conductors. The power loss due to voltage drop is proportional to the square of the current, so a higher current due to a low power factor results in significantly higher losses. This not only wastes energy but also increases operating costs. Thirdly, a low power factor can overload transformers and other electrical equipment. Transformers are rated in kilovolt amps, which is the apparent power. When the power factor is low, the apparent power is much higher than the real power, meaning the transformer is being loaded closer to its kilovolt amp rating even though it's delivering less real power. This can lead to overheating and premature failure of the transformer. To mitigate the negative effects of low power factor and excessive voltage drop, several strategies can be employed. One of the most common and effective methods is to use power factor correction capacitors. Capacitors supply reactive power to the circuit, effectively cancelling out the inductive reactance and improving the power factor. By reducing the reactive current, capacitors lower the overall current flowing through the conductors, thereby reducing voltage drop and energy losses. The size of the capacitor bank needed depends on the amount of reactive power required to achieve the desired power factor. This can be calculated using power factor correction formulas and considering the load characteristics. Another method for improving power factor is to use synchronous condensers. Synchronous condensers are essentially synchronous motors that are operated without a mechanical load. By varying the excitation current of the motor, the amount of reactive power it supplies can be controlled. Synchronous condensers are typically used in large industrial facilities where significant power factor correction is needed. Improving the overall system design can also help to minimize voltage drop and improve power factor. This includes using larger conductors to reduce resistance, minimizing the length of conductors to reduce both resistance and reactance, and using transformers with lower impedance. Additionally, it's important to properly size electrical equipment to match the load requirements. Oversizing equipment can lead to increased losses and a lower power factor. Regular monitoring of power factor and voltage levels is also essential for maintaining an efficient and reliable electrical system. Power quality analyzers can be used to measure these parameters and identify potential problems. Based on the measurements, corrective actions can be taken to optimize the system performance. In summary, a poor power factor has a significant impact on voltage drop, leading to reduced voltage at the load, increased energy losses, and potential equipment damage. By implementing power factor correction techniques and optimizing system design, these negative effects can be mitigated, resulting in a more efficient and reliable electrical system. Furthermore, it's crucial to understand the economic benefits of power factor correction. Many utility companies charge penalties for low power factor, so improving the power factor can result in significant cost savings. Additionally, reducing energy losses and extending the life of electrical equipment contribute to long-term cost reductions. In addition to the techniques already mentioned, there are other advanced methods for power factor correction and voltage drop mitigation. Active harmonic filters, for instance, can improve power factor by reducing harmonic currents in the system. Harmonic currents are non-sinusoidal currents that can distort the voltage waveform and increase losses. Active harmonic filters use electronic components to inject compensating currents that cancel out the harmonic currents, resulting in a cleaner power supply and improved power factor. Another advanced technique is the use of static var compensators, SVCs. SVC are shunt-connected devices that provide dynamic reactive power compensation. They use sires to control reactors and capacitors to rapidly adjust the amount of reactive power supplied to the system, maintaining a stable voltage and improving power factor under varying load conditions. SVC are typically used in large industrial facilities and transmission systems where voltage stability is critical. In addition to these hardware-based solutions, software-based solutions are also available for power factor monitoring and optimization. Power management software can analyze real-time data from electrical equipment and provide recommendations for improving power factor and reducing energy consumption. These software tools can also be used to simulate the effects of different power factor correction strategies, allowing engineers to optimize the system design. When implementing power factor correction, it's important to consider the potential for overcorrection. Overcorrection occurs when too much capacitive reactance is added to the circuit, resulting in a leading power factor. A leading power factor can also cause problems such as increased voltage and instability in the system. Therefore, it's important to carefully size the capacitor bank and monitor the power factor to ensure it remains within the optimal range. Another important consideration is the location of the power factor correction equipment. Capacitors can be installed at the individual load, at the feeder, or at the main service entrance. Installing capacitors at the individual load provides the most effective power factor correction, as it reduces the current flowing through the entire circuit. However, this may not be practical for all types of loads. Installing capacitors at the feeder or main service entrance is a more common approach, as it's easier to implement and maintain. In conclusion, power factor correction is an essential aspect of electrical system design and operation. By understanding the relationship between power factor and voltage drop, and by implementing appropriate correction techniques, it's possible to significantly improve the efficiency, reliability, and cost-effectiveness of electrical systems. The selection of the appropriate power factor correction method depends on the specific requirements of the application, considering factors such as load characteristics, system size, and cost constraints. Regular monitoring and maintenance of power factor correction equipment are also crucial for ensuring long-term performance and reliability. Furthermore, with the increasing adoption of renewable energy sources, such as solar and wind power, power factor correction is becoming even more important. Renewable energy sources often have variable output and can introduce harmonic currents into the grid, which can negatively impact power factor. Therefore, advanced power factor correction techniques are needed to integrate renewable energy sources into the grid while maintaining power quality and stability. In addition to the technical aspects of power factor correction, it's also important to consider the regulatory requirements. Many countries and regions have power factor standards that require industrial and commercial facilities to maintain a minimum power factor. Failure to comply with these standards can result in penalties and fines. Therefore, it's essential to be aware of the local regulations and ensure that the electrical system meets the required power factor standards. The implementation of power factor correction not only benefits the individual facility but also contributes to the overall efficiency and stability of the electrical grid. By reducing losses and improving power quality, power factor correction helps to reduce the demand on power plants and transmission lines, which can lead to lower electricity prices and reduce greenhouse gas emissions. In summary, power factor is a critical parameter in electrical systems that affects voltage drop, energy losses, and equipment performance. By understanding the principles of power factor correction and implementing appropriate techniques, it's possible to optimize the performance of electrical systems, reduce costs, and contribute to a more sustainable energy future. The selection of the appropriate power factor correction method should be based on a comprehensive analysis of the system requirements, considering factors such as load characteristics, system size, cost constraints, and regulatory requirements. Regular monitoring and maintenance of power factor correction equipment are essential for ensuring long-term performance and reliability. As technology advances, new and innovative power factor correction solutions are being developed, offering improved performance and cost-effectiveness. These solutions include advanced capacitor technologies, smart grid technologies, and artificial intelligence-based power management systems. By staying informed about the latest developments in power factor correction, engineers and facility managers can make informed decisions and implement the most effective solutions for their specific needs. In addition to the benefits already mentioned, power factor correction can also improve the lifespan of electrical equipment. By reducing the stress on equipment caused by excessive current and voltage fluctuations, power factor correction can help to extend the life of motors, transformers, and other electrical components. This can result in significant cost savings over the long term. Furthermore, power factor correction can improve the stability of the electrical system, reducing the risk of voltage sags and surges. Voltage sags and surges can damage sensitive electronic equipment and disrupt operations. By maintaining a stable voltage, power factor correction can help to prevent these problems. In addition to the economic and technical benefits, power factor correction can also improve the safety of electrical systems. By reducing the risk of overheating and equipment failure, power factor correction can help to prevent electrical fires and other accidents. Therefore, power factor correction is an important aspect of electrical safety. In conclusion, power factor correction is a multifaceted topic with significant implications for electrical system performance, efficiency, and safety. By understanding the principles of power factor correction and implementing appropriate techniques, it's possible to optimize the performance of electrical systems, reduce costs, improve safety, and contribute to a more sustainable energy future. The selection of the appropriate power factor correction method should be based on a comprehensive analysis of the system requirements, considering factors such as load characteristics, system size, cost constraints, regulatory requirements, and safety considerations. Regular monitoring and maintenance of power factor correction equipment are essential for ensuring long-term performance and reliability. As technology continues to evolve, new and innovative power factor correction solutions will emerge, offering even greater benefits for electrical systems.